Hello and welcome to the 16th clinic in linear algebra. Today we're going to be looking at row space, column space, null space, and then the rank of a matrix as well as the nullity of a matrix. All right, find the basis of the row space of this, 3x4 matrix, and then we want to calculate the rank. Okay. So what we're going to do is take a look at the matrix. Now let's RREF it. So the non-zero rows will form a basis. And so this forms a basis for erasing everything. Or let's call it row space of A, which means, right, that the rank of A is just the dimension of the row space. So it's 2. Here we want to find a basis for the row space of this matrix. I think this is what, 4x5? And then calculate the rank of B. So it's the same thing, right? So start with our matrix, and then we'll go ahead and row reduce it. Right, once again, the non-zero rows will form a basis. Again, let's just call it row of B, which of course means that the rank of B is a dimension of the row space, and hence the rank is 2. So next we're asked to find a basis for the row space and the null space. And then we're asked to calculate the rank and nullity. Right? Okay. In both cases, what we're going to want to do is row reduce the matrix. So RREF this. So again, the non-zero rows of this matrix is a basis for the row space. Let's call this basis for row. All right, so the first row second row, and the third row. So this means that the rank of C is 3. Now, if we look back, the non-zero columns will form a basis for the null space. So first is 2, 0, 0, 0. Then we have -1, 3, 0, 0. I'm sorry, I said the non-zero columns. I meant columns without a leading 1. Let's call that null of C. Well, the nullity of a matrix is the dimension of its null space. So our null space has dimension 3, and hence the nullity of this matrix is 3. As let's suppose that U equals A1, A2, AN is the linear combination of the rows R1, R2, Rn of a matrix B. We want to prove, right, that A sub I is equal to that. Right, so we know that U is going to equal K1 R1 plus K2 R2 plus so on and so forth, right, plus Kn Rn for each K being a real number. I'm sorry. It should be Km Rn. All right, so this implies this would equal K1 times the first row plus K2 times the first row. I'm sorry, times the second row. Plus so on and so forth up to Km times the mth row. Right, which equals K1 B11 plus blah 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 plus Km BM1. Right, that's the first row. Right, and that's going to continue until we get to the mth row, and we get K1 B1N plus so on and so forth plus Km BMN, right? So in order for matrices to be equal, rows have to be equal. So we get at AI is K1 BI1 plus K2 BI2 plus so on and so forth. No, I'm sorry. K1 B1I plus K2 B2I plus so on and so forth plus Km BMI. Right, for I equal to 1, 2, up to N as desired. The AB N by N matrix, we want to show that A is invertible if and only if the rank of A is 0. I'm sorry, if the rank of A is equal to N. So if A is invertible, then this means that A is row equivalent to the N by N identity matrix, right? Which means that A is row equivalent to a matrix with no 0 rows. That means the rank of A will be 0, not 0, will be N, right? Every row is not a 0 row. Now let's suppose that A is not invertible. Then A would be row equivalent to an N by N matrix with a row of zeros. Which means the rank of A will be less than N. But that means that the rank of A is not equal to n. Right? So if it's invertible, the rank has to be n. If it's not invertible, the rank cannot be n. Right? So this means that A is invertible if and only if the rank of A is equal to n, which is what we wanted. Okay, and that will conclude today's clinic. Next time, we will take a look at change of basis. All right, so we'll look at coordinate vectors and change of basis matrices. Thank you, everyone, for attending. Thank you for watching. I will see everyone again in the next clinic.